younger students who are here start to learn about the research opportunities in the department. So what we have planned for the next hour is all the faculty members who are interested in engaging undergraduates in their research are here to talk in one way or the other, just to give you some idea of who they are, what their face is, so you know who to talk to. And everyone has about 5 minutes just to talk quickly. It's not enough to kind of completely tell you what they do, but quickly give you some idea of what type of research they're involved in. You're still going to have to go find out more about them at your leisure, but at least you know who we are, where to find us. And then I also have some students here. I've asked Travis and Emma from the Physics Club and Xiao, graduate student, to talk about what they perceive as the value of undergraduate research. So there's really two questions that I see when the first and second year students are talking to me, which is, one, why should I even do research because I'm busy anyways? Isn't that just taking up some of my time, and why should I at all be involved in that? I think they will be able to really talk about what it's done to augment their education and how it really will help your career. And then two, the next question is, well, I'm interested, but how does this happen? How do I get started? How do I find out what people do? And that's what the professors will be able to talk to you about today. So that's our goal. So it's just information, and then we assume that the conversation will continue beyond this. It should be going forward through the next coming weeks up till the summit. Okay. So we have 8 faculty members here who are ready to talk about the most excellent things that we do. So I don't know who wants to start. We should Rochambeau for you or something like that. So does anyone have a thought? TJ, you want to
sure.
take us on the road? I'm recording this, so for the people who aren't here, I'll probably put it on our YouTube channel. So if you have colleagues who are not here, friends, just tell them that they can watch all of this on YouTube. I don't know how well they'll be able to hear it, but we're recording it up here, so if you kind of stay in this way here and talk about what they're doing, and just roughly about 5 minutes per person, so that should be about 40 minutes for the faculty. So, thanks.
Okay, so my name's TJ Hammond. I have a group down in the basement here, basically 2 floors directly below. I guess I could go on screen. We call it the ACME Lab. It stands for Attosecond Condensed Matter Experiments Lab. So as I said, it starts off with attosecond. So what I do is I study time-dependent phenomena. And so it has the word second in it, so you can think that it's something to do with time. It's an attosecond, so it has this prefix atto, which you probably haven't heard of before, but an attosecond is really, really fast. It's a billionth of a second, so 10 to the minus 18 seconds. So if we think about things that are kind of used to for how fast things go, we have a year, and so the Earth orbits around the sun, and it takes a year, or it's about 3 times 10 to the 7 seconds. Something you guys are probably also familiar with is like a microprocessor. So these work at like a gigahertz. So a processor works at about 1 billion times per second or so, something like that. And something even smaller than that is like small molecules. So here we have like a CO2 molecule as it's tumbling through space. This rotation happens on picosecond timescale, so 10 to the minus 17 seconds. Or you have even something faster, which is the vibration of a molecule that happens on 10 to the minus 15 seconds. So this is a millionth of a billionth of a second. But what we do is we study stuff that's even faster, and that would be if you had like the Bohr model of an electron that's orbiting around a proton, like this, like what you guys have probably seen before. This orbit takes, instead of a year, it takes about 150 attoseconds for it to complete. So this is kind of like a rough model. This is a classical picture, but this is about the time scales of the stuff that we're looking at. So what we're doing is, instead of quantum mechanically, I want to play this video. So this is a simulation of what we're trying to do. And what we have here is, instead of this electron orbiting around the sun, it's actually an electron wave packet. So when you guys get to 3rd or 4th year, you'll start to learn about quantum mechanics. And instead of seeing these electrons as these solid like balls, it's actually a wave packet. And what we're doing is we're coming in with a laser field, and we're strongly moving this electron wave packet around with this laser field. And so what I want to do is combine these really, really fast processes that we can do controlling an electron wave packet with a laser field, and also control that with really, really small distance scales. So you guys have probably seen images like this, that you see something that's like a few nanometers or a few microns in size. So this is like from like an atomic tip or something like that as you scan across. And so what I'm trying to do is combine this idea of looking at something at the nanoscopic or microscopic spatial scale, and then also something that's working at the attosecond and femtosecond time scale, and combine those two fields together. So that's my research. So what we have, by doing this, we've developed a whole bunch of different tools. And so we come in with these really strong laser fields, and these really strong laser fields allow us to do a whole bunch of different tricks and techniques to try and understand these electron wave packets. So we have these things we can reconstruct waveforms. So these electric fields that we have coming out of lasers, we can actually measure those fields directly. These strong fields can also create new kind of frequency components. It's called high harmonic generation. We can combine these with different types of materials. So we can have gases, we can have liquids and solids. And now we're starting to look at nanoparticles. So this picture here that we have is from a paper that you can see that this is a 5 micron right here. This is 5 microns here. So it's 5 micrometers in size. So it's really, really, really small. And so the width of these things here is something like the width, like a 20th of the width of a human hair. And we have these little electrodes that are really, really thin. And then we shine a laser beam on them, and then we can control these electrons moving around within these wires. And we can send signals this way. And this is how your phone works, or a computer works, or something like that, is you send these electronic signals really quickly. But it turns out we can send these signals about 1 million times faster than what your computer or your phone can do right now. So this is some of the research that we're doing in my lab, or this is what we're trying to develop in my lab. And this is a poster actually from Travis here. So this was his project last summer, was kind of simulating what we're trying to do in the lab. So what he said was simulating attosecond experiments with an Arduino-controlled LED. So what we have are these really, really fast laser pulses, and we're hitting these electron wave packets. That's what we want to do in the lab. And so in order to kind of develop a simulation for this to kind of explain how this stuff works, Travis developed this system with a pump that drips out water droplets at a regular interval, and then he flashes these water droplets with a strobing light, with an LED strip that he can computer control. And it makes it look like these water droplets are suspended in air, even though they're falling, of course. But if you take a flash right at the right time, it makes it seem like these water droplets, they're positioned in space, and then as they fall, you turn off the light, and then when they come back, when the next drop of water comes to that same spot, you take another flash. And in the strobing, this light makes it look like these water droplets suspend in air. And so this is the point of this project. And so in order to do this, you have to program these Arduinos and develop all these kind of electronics and stuff like that. But those are the kind of experiments that you can do as an undergrad working in my lab. And I think that's about my 5 minutes. So thank you very much. And if you guys want to see this working, Travis will show you down in the lab, which is about 2 floors down.
And what is the best way for a student to find you if they want to talk to you?
My office is just across the hall here in 289-5, or come find me in my lab, again, in B90.
Okay, so there you go. Dr. Hammond. Who wants to go next?
I can go next.
Dr. Ng.
Okay, hi everyone. My name is Chitra Rangan. I'm one of the profs here. And my students and I, we work in the area of quantum control and nanophotonics. So what does this mean? We basically develop theories of how light will interact with atoms, molecules, or gold nanoparticles. So these are all the size of nano, or 10 to the negative 9 meters, or smaller. And the idea being that if you take light is composed of many colors, but if you can add specific amounts of colors and shape the light, then you can control this interaction. You can change how this light interacts with different quantum systems. And so that's the whole overarching goal of my research program. Some research questions that we study. What happens if you take a whole bunch of atoms together and cluster them and then shine them with ultra-fast light or a very strong pulse of light? So we found that you can actually make these atoms behave much more randomly than if you just had the atoms individually. I had Luca was working with me for a couple of semesters on designing a biosensor using gold nanoparticles that can detect diseases early. This is a project that I don't know if you guys know Candace Fast, who graduated last year, and now Rory Sutcliffe is working on this idea where how do you take ideas from physics and then map it to linguistic studies. So how do people think of relate words in everyday language, and how do people who relate words differently when their brain is injured? And this is a project that Zach Manson is working with me on how do you produce specific shape pulses called adiabatic controls, and that can help to make better quantum computers. So it's a whole range of questions, but the whole general idea behind them is how does light interact with matter, and how do you design specific light pulses to interact in a specific way to control the interaction. So students usually, I said we're theorists, so students will usually do pen and paper calculations, or they will do computer simulations, or a combination of both, depending on what their strengths are. Who can do research? So we're trying to attract the undergrads who are here, but students, you don't have to think that you have to be in some program to do research. Anybody who wants to do research can just do research. So, for example, most of the time the students who start working for me come as outstanding scholar students, but if you're not an outstanding scholar student, it doesn't matter, you can still do research. There's a honors thesis course in the 4th year where you can do 2 semesters of research and get course credit for it. You get 2 courses credit for it. The NSERC USRA is a scholarship program. It's competitive, but you can apply for that. And last year I supervised Luca for his NSERC USRA scholarship. He was a first-year student, so anybody can actually apply for that. The scholarship deadline is coming pretty soon, so I would encourage everyone who has 80% and above average to apply for that. You could also maybe apply for Dr. Bayless's scholarship. So there's a Bayless Research Scholarship also, which gives you a little funding to have the opportunity to work with a prof. There is an undergraduate research course for 3rd year and 4th year students, where if you're not doing a complete thesis, you can work for 1 semester on a research project. I have a math student who's currently doing that with me. You could also be a summer research assistant or a co-op. Usually, I hire students, this is usually a paid position, so I hire students if they have done volunteer work with me before, so I know what they're capable of doing. So they're able to give me something, do something that, so my students usually spend a minimum of 1 year, but usually 2 or 3 years with me. And by the end of the time they finish their research, they contribute to a publication, and they definitely go and present at conferences as well. Other people who are in the group are usually master's or PhD students. These are called graduate students. Postdocs are sort of like medical residents, so they already have a PhD, but they're not a full professor yet, so they're sort of in between there. I also do physics education research, so some students who work on that aspect, then they get service learning credit for that. And as I said, we are theoretical physicists, so our goal is to model phenomena mathematically, and then you solve equations as much as you can with pen and paper, and then when you can't do that anymore, then you make a computer simulation. But the main point is to make sure that your computer simulation or your answers, they give you back the solution to the real world problem that you're trying to answer. Okay, and so I encourage everyone to come talk to me. So these are my coordinates. My office is around the hallway. It's the 2nd office in that hallway. Or my email address is just my last name at UWindsor.ca. So thank you.
So yeah, I should point out for people who don't even know it all, typically most of the research physicists in the department, physicists everywhere, are either experimental or theoretical in general. It's one or the other. So Dr. Hammond is obviously an experimentalist. He has a lab where you're building things on stairs. Dr. Rangan is a theorist, so they, as she said, they use computers and calculations and pen and paper and things like that. So we'll try to make sure that that's clear to you, although you can go into whichever field, doesn't matter what you're interested in or what you think your talents are yet. So we just heard from theorists, so maybe let's start with another theorist, Dr. Kim. He's got his presentation up over here since he was just teaching, so he's going to be speaking over here. So Dr. Kim, another theorist in the department, then maybe we'll go back to an experimentalist after that to keep you on your toes.
Okay, so my name is Eugene Kim, and in general, I'm interested in collective phenomena in condensed matter systems. So, well, how does this come about? So I'm interested in systems materials. So these have, order 10 to the 23 particles, or more generally, degrees of freedom. And when you start letting them interact and combined with quantum mechanics, some interesting things can arise. And some of the things that arise has been eloquently described as a quantum waltz. Namely, you literally get these dancing-like, when you analyze it, you can think of them in terms of these dancing-like patterns. Okay? So my current research focus is on information theoretic characterization of exotic quantum phases, so I will elaborate on this. And quite a bit of my work involves systems out of equilibrium. Okay? So a key means by which I've been using to characterize these systems is entanglement. So entanglement expresses the spooky non-locality inherent in quantum mechanics. So spooky, this was actually dubbed by Einstein. So if you consider a system that's comprised of two subsystems, so this could be, actually two systems, or something where you at least mentally break it up into two subsystems. Okay? So classically, to know everything about this, you just specify the properties of system A and system B. Now, in quantum mechanics, there's more to the story. Ultimately, it simply arises from superposition, but, that leads to all kinds of interesting things that can come out. Okay? And entanglement, so how did people like me get interested in using entanglement to characterize these systems? Well, roughly speaking, so entanglement is the central resource in quantum computing. Now, if you actually want to build a quantum computer, you need, so the central element of a quantum computer is a so-called qubit, just some type of two-state system. But if you actually want to build an actual quantum computer and do some type of computation, you need, you can't just have one of these, you need many of them. Okay? And now once you stack many of these together, essentially by definition, you have a condensed matter system. So roughly speaking, historically, this is how people like me got interested in this. People in the quantum information community start looking at these multi-qubit systems, and in their characterization, people in my community realized that there's some interesting things one can do with this beyond what we were traditionally doing. So that's how this entered into my community, and I got involved in this. Another key measure I've been using recently to characterize this system is something called complexity. So here, the question we want to address can be stated very simply. We have some reference state, and we have some target state. So we have some place that we start, and we have somewhere we want to go. And we ask, what is the optimal way to get from here to here in some sort of time, if you will. So what is the optimal, the technical term we use is quantum circuit, to get from where we start to where we want to end up. And the complexity, the definition of this, is the minimum number of steps we need to get from our starting point to our final point. Okay? So how did this has been a well-studied area in quantum information. How this came to prominence in my area of work is due to Leonard Susskind in what may seem like a very different way, but there's a technical step relating it. So he was motivated by this question. If you consider a black hole, and in particular the evolution of a black hole, after the black hole thermalizes, it appears there has to be some quantity that continues to evolve. And Susskind conjectured that it's the complexity that continues to evolve. So now, how does black holes have to do with, I noted that I'm interested in materials, quantum materials. There is a technical step in getting from black holes to that. But nonetheless, you take that technical step, and it's in this way here that complexity came to prominence in the types of systems I am interested in. Okay. So well, I've been participating in what could be described as a successful marriage, namely this marriage of condensed matter and quantum information. And so there has been just an incredibly rich interplay between the two, and the consequences have been just absolutely not just far-reaching, I would go so far as to say mind-blowing. Okay? So, all right, so my key interest is in characterizing exotic quantum phases using these measures, information theoretic measures. So exotic quantum phases, this means different things to different people. Let me tell you what it means to me, well, the types of things I'm doing. I'm particularly interested in these systems where it looks like the fundamental degrees of freedom break apart. So it turns out in one-dimensional metals, it looks like the electron has ripped itself apart. Namely, the charge flies off and the spin just trudges along. Okay? Another family of systems I'm interested in, it looks like, roughly speaking, the electron has, here we're interested in, if you will, spin polarized systems, so get rid of the spin degree of freedom, and roughly speaking, it looks like the electron has ripped itself in half. So again, exotic means different things to different people. These are the types of systems I am particularly focusing on and working to characterize using these information theoretic measures. Okay? So some current work I'm involved in, one is characterizing so-called multi-channel Kondo systems using information theoretic measures. So the Kondo problem, this is a classic problem, a very, very deceptively simple problem, but, well, truly deceptive. So the classic Kondo problem involves just a single magnetic impurity interacting with a bath of conduction electrons. Okay? So you have order 10 to the 23 conduction electrons interacting with this one silly magnetic impurity, and so one might ask, what could this one thing do to order 10 to the 23? Okay, so on the surface, you'd say not much, but with a moment's thought, you realize, well, some interesting things can happen. Why? So you can have a conduction electron, at least semi-classically, you can think of it as some conduction electron coming in. It'll scatter off of this, and in doing so, it flips its spin and the spin of this impurity. Now, at a later time, another electron can come in, scatter off it. In doing so, it flips its spin and the spin of the impurity. Okay? And this keeps happening, on and on. Now, with a moment's thought, you realize what this does, what this single magnetic impurity has done, because of all these scattering processes, is in fact established correlation with the entire bath of conduction electrons. Yes, this one single magnetic impurity can influence this entire bath of conduction electrons because it has this internal degree of freedom that can change. Okay? And so, well, this here is understood, but if you start generalizing the problem, so for example, if somehow you manage to have two conduction baths, like I'm trying to show here, now how you do that is non-trivial, but if you do manage to do that, and we have some ideas on how to do it, you can get some really interesting things happen. So if you can set it up like this in some type of circuit, where this is your magnetic impurity, you can get a situation where you have vanishing charge conductance. Okay? So you have zero current, charge current flowing through this, but this is a perfect spin conductor. So spin excitations can propagate freely. So it's a perfect spin metal, but a charge insulator. So you can have, interesting things like this happening, and my work is, something I'm working on is to characterize this type of system and these phenomena using measures of entanglement and more generally measures from information theory. Okay? Maybe I'll skip this one. Another thing that I've been pursuing quite actively is complexity and entanglement of fermions on what's called anti-de Sitter space. And okay, so very quickly, there's a condensed matter model. There's a condensed matter model where it turns out, quite remarkably, it is a so-called lattice regularization of fermions on anti-de Sitter space. So anti-de Sitter space is very, very popular, if you will, in the high energy community. And this work has a very cute title, working title, the rainbow connection, because this condensed matter model is the so-called rainbow chain. So this was a surprise, that this condensed matter model, this chain called the rainbow chain, actually is a lattice realization lattice regularization of fermions on this space. And so some collaborators and I, we've been working to use measures of entanglement and complexity to characterize various properties of fermions on any de Sitter space. Okay, so that's a glimpse of some of the things I'm doing, and I apologize I went over.
Sounds good.
And how do you prefer that they find you?
My office is, I guess, right next to TJ Hammond's. So either before talking to him or after talking to him, you can come to my office. Or you can reach me by email. It's just my first two initials, EH, and then my last name, K-I-M. So Professor Rangan just used her last name. There are too many Kims, so I put my first two initials, and then UWindsor.ca.
You can find us on our website too. So we're all there. Now you've seen our faces, and now you can just click and hit send. Very easy. All right, so that's theory. Let's hear from experimentalists. So I'll ask Dr. Maev is here, and he will talk to us about what he's doing.
Thank you.
Thank you.
I'm already in stress because you're pretty strict with the time. And
I didn't bring the hook.
I will try my best to do it during 5 minutes, yeah. But before I will maybe introduce what is about us and our interest. I have no presentation like that because it's difficult for me to do this because I have about 16 projects currently in my organization. And what we are, it's just to let you know that our university have 3 research institutions which concentrate on a kind of big problems. Most youngest, it's a cross-border institute, which was created by simple reason because we are the border city, and they their research related to security, to economical, to social, to logistic, and so on problem. So, and for that reason, they communicate with mostly with Department of Business School, with economical department, legal department, so on. So, just explain you the idea. We have another big research institute, which is most oldest. It's a Great Lake Institute, which also, by name, you understand what it's about. They care about Great Lakes. Without our Great Lake Institute, Great Lake will disappear or something happens wrong with them. So it's a lot of problems related to ecology, related to some hydro and air conditions, and some many problems from cells up to the big scale. And of course, they affiliated with biological department and with chemistry, biochemistry. And it's already, they celebrated last month 25 years old, how they was created. Institute for Diagnostic Imaging Research strongly affiliated with the physics department for many reasons, including that I'm professor in physics. And we passed through 10 years, and it's mostly focused on based on the name of imaging. And we're doing whatever possible to do with imaging. It's about 35 people working in this organization. And what you can expect from such organization, we need to be very professional with image processing. We need to know how to work with image, how to make segmentation of image, how to filtrate image, how to remember, how to do image recognition, and so on. And each of that stuff required a lot of mathematics, a lot of electrical engineering knowledge, a lot of physics knowledge. And for that reason, it's the same as other organizations which I mentioned. We are multidisciplinary. So for that reason, we have different students from computer science, from electrical engineering, mechanical, biology, and of course, my majority of our students, it's kids from physics department. So we have some basic problem which we developed through the image signal image processing, and also there are a lot of unique applications which we involved. So just an example for you, but for example, image recognition, security, and we had a big project from Air Canada and organization related to aviation to create security at the airports. So, look like it's a kind of simple problem, and people already develop this in different countries. But in Canada, it's not so much developed, and the idea was that we need to recognize not only your faces, which is already kind of routine work and people doing that, but recognize your behavior in real time. So I need to predict if you hug me, or if you want to hint me, or you want to punch me, or I need to do it right away in real moment. And if something, my system recognizes that something wrong with you, they need to immediately send signal to the guards, and they will come with the gun and stop you before you kill me. So it's a little bit kind of excited topic, unusual, but for students it's a big fun. And we install such system at Sudbury, which predicts your behavior. And I don't know what happens in the future, because we're university. We not move forward with that. We just show the product. We're excited. We did publication, and that's it. Another also related to imaging stuff, which we're really excited to do. It's related to classical physics problem, inversion problem, how to receive the image and after that inverse them to completely different format. And one of the simple example of that, if you have brain injury diagnostic, so usually only one way today to put a proper diagnosis is you need to do CT scan. So, but in harsh environmental condition, or let's say big natural disaster, or it's a military operation, or it's just big accident, if you have a brain injury, you need to have immediate help. I need to give you, even if we are paramedical guy, we need to come and put proper diagnosis, and after that, treat it properly. There is so named gold hour between when we discover that you have trauma and when you, sorry to say, passed away. So if during that hour you can help, you will be alive. If not, sorry. And so we in development of such system which can be portable, easy to manipulate, and give you a proper information about that. Where is the problem? Problem that you cannot bring CT scan or MRI to the field. So because we are kind of guru in ultrasound, we decide, okay, can we do it ultrasound? But if I send ultrasound through the skull very irregular bone, and it's a kind of screen which can kill ultrasound. They do very strong refraction, they give strong aberration, and when you send signal through that screen, you will not receive anything. So you will not receive anything if you don't know the secret of inverse resolve inverse problem. First inverse problem was resolved in for the problem from undergraduate underwater acoustics it's just in the 50s, just after Second World War, and people received the Nobel Prize for that because it's really complicated from physics and mathematical point of view problem. Second problem, just example for you, it's astrophysics. How you know that your stars is blinking, but it's because it's there are a lot of screens between stars and you which breeding, and that's how the results of not quality image. So that's what, and we resolve the third problem when you can pass ultrasound through the irregular signal, and we can receive them, reinverse them, and rebuild them, and we have pretty clear image. So it's a very serious problem. We work on that almost 10 years. Today we have prototypes, and behind that wall there is our lab where we can bring the heads of ships, poor ships, and manipulate with them with ultrasound, and we can see we can see in real time what happens with the brain and how we can fix it and how we can put. But I just told you about that 2-3 examples, but as I said, we have 16 projects, and how to work with us for undergrad kids. We developed this already maybe 10 years. We have a so-named summer school, which very strong supported by department, We can recruited about 10 to 15 kids every summer for May, June, July, August. And if you're interested, you just need to contact us. We start collection of candidates in February, March. I personally interview each of the kids who is interested to come, and we can direct them for particular project which we run at that time currently. And during that 2-3 months, you will be familiar with the particular problem, and obviously you need to defend your small project, and after that it's your decision. If you want to continue, if you have the position for that, if not, it's up to you. But at least it's a chance for you to learn a little bit more, and plus it's fun. We have it's a camp with 15 kids, and it's a pleasure to work during summertime. So welcome. Yes, thank you.
Thank you. So yeah, send Dr. Maev email. Again, contact information is there. But Dr. Maev spends a lot of time at the IDIR's Institute of Diagnostic Imaging Research, which is off campus here. So if you don't see him, it's harder for him to find in the office. I think email would be better. Right?
Thank you.
Yeah. All right. Well, let's go to theory since we're mixing up to experiments. So maybe Dr. Rao is sitting there patiently. So let's turn the floor over to him and see what he has to say about some things.
Thank you for that very non-specific introduction.
Not specific as I can be.
Yes. Okay. No. Come on. Okay. Well, that's close enough for now. Spend all the time watching me struggle with Microsoft's web browser. So I'm Jeff Rao. So I'm a theoretical condensed matter physicist who mostly works on anisotropic frustrated magnets. And so since some of you, a good chunk of you are first years, let me break down what that means. Normally when you think about the progression of physics, you probably think about it as things are getting smaller or faster, attoseconds, for example, or you break down matter into molecules and atoms into protons, neutrons, electrons, protons and neutrons into quarks, quarks into whatever. Condensed matter comes at this from the other direction. Instead of asking what happens when you divide matter up more finely and finely, it asks what happens when you put more matter and more matter together, right? And so this can give rise to whole new kinds of phenomenon. So even if you know what an electron is, if you know what a proton is, even if you know how they're arranged in something like a solid or metal or material, it's still hard to predict what happens when you put them all together. So for example, we knew all of these things in the 1920s and 1930s. It still took 30, 40 years before we understood how superconductors work, right? So even if you have all the ingredients, when you put them together, you can get new and fundamentally interesting things. So my work is mostly on magnets and mostly on realizing new phases of matter. So these are magnets which are related to, but we're videotaping this. Related to, but somewhat distinct from, what you would think of a magnet, a fridge magnet. A fridge magnet is made of, little particles, atoms, which each have their own little magnetic moment. A magnet is an array of little magnets. So these can come in all sorts of different flavors, and they can exhibit all sorts of different phenomena. So as Dr. Kim mentioned somewhere in his presentation, these can give rise to whole new kinds of phases of matter, which can give rise to particles and phenomena that you wouldn't obviously expect from the fundamental ingredients. So you can get things where you have a magnet, it's just some relative of the fridge magnet you stick to your fridge, and then inside it, the behavior of these little fluctuating magnets resembles something like magnetism, like electromagnetism, complete with light, complete with a photon, all happening inside of material. Okay, so my work specifically is on these things in anisotropic magnets. So these are magnets made of typically heavy elements near the bottom of the periodic table. This lets you have more kinds of interactions, more kinds of physics, more kinds of things just showing up. Practically, I do a lot of work on connecting these things with actual experimental realizations. So things like talking to experimental groups, analyzing data, coming up with new structures, new geometries that might better realize this new and exotic physics. So I just started here maybe 6 months ago, so my group is still under construction. So what it looks like is to be determined. But I have a lot of problems that I'm interested in looking at that I think could be made accessible at the undergraduate level. Watch me struggle with the computer briefly. So things like looking at how the constituents of magnets interact and how we can tune that to enable this new physics, and understanding in more detail how the excitations of magnets work, what happens when you shoot them with light, when you shoot them with neutrons, and what that can tell us about what is observed experimentally. So if you're interested, please get in touch. My office is directly outside those doors. You can also email me. My email address is jrao@uwindsor.ca.
All right, thank you very much, Dr. Rao. I think I'm going to turn the floor over to Dr. Drake here.
Okay, get mine. Yeah, there we are.
The appropriately
Okay.
named grad talk.
Good.
I'm gonna, now we let Dr. Drake
Yeah, okay.
with Microsoft. That'll be fun.
Okay, thank you, Steve. Yeah, my name is Gordon Drake. I'm a professor emeritus, which means that I no longer give regular lectures, but I'm still very much involved with research. I don't have to sit on committees, and so that gives me a lot more time to do research. And so my area is high precision atomic theory. So I'm going in the opposite direction of, instead of seeing how complicated we can make things, how simple we can make things, and still look for fundamental new atomic physics. So my current research group, I have 2 PhD students, 1 master's student, and 2 undergraduate students, Habir and Victor, who are both there at the back of the room. And so we meet to discuss their research project on a fairly regular basis. And so the goal is to solve the quantum mechanical few body problem, which is a generalization of the classical problem of let's say, a sun and 2 planets. That's a 3. You can solve a sun and 1 planet. That's the classical Kepler problem. As soon as you have 2 planets, it can no longer be solved exactly. And so just making it quantum mechanical doesn't make it any easier. So our goal is to solve the quantum mechanical few body problem with just 2 electrons, 3 electrons, but including higher order corrections, including relativistic and quantum electrodynamic effects. The quantum electrodynamics is the interaction between electrons and photons, with all these fields being quantized. And this gives rise to new physics beyond the Schrodinger equation or its relativistic generalization. And so our aim is to look for evidence of new physics beyond these simpler starting points. The motivation, this is the oldest part of modern physics. That's where it all started with first Planck's theory of black body radiation, and then the Schrodinger equation. This is all based on properties of atoms, the simplest atoms, hydrogen in particular. And so why is this still interesting? What is the motivation for still being interested in basic atomic physics? And so there are 2 answers to this. Let's see, how does this go? Let's see, how do we do? Oh, I use this one, I guess.
No, just scroll it with the wheel on the mouse, I think.
Scroll it with what?
The mouse?
The mouse? Oh, this one.
Yeah, just scroll with the wheel, I think.
Wheel. Let's see. The wheel isn't doing anything.
No. You gotta click it first.
Click.
I guess just do the slide.
Click, turn.
Yeah, it's not on any kind.
Yeah, I tried the arrows don't work.
No, I don't think so.
Yeah.
So just use the rolling thing on the mouse.
Just
I see. Scroll that way. Okay.
the wheel.
Okay, so the two basic answers. Roll. First is the search for new physics beyond what's called the standard model. A standard model combines electromagnetic theory, electromagnetic interactions with the weak interaction, the strong interaction of nuclear physics. Put this all together into one big model that accounts for just about everything we know about the fundamental interactions. But new particle accelerators are becoming more and more expensive to build in order to search for new particles. And so there's a lot of interest now, such as clues about dark energy, dark matter, and these things. So there's a lot of interest now in instead of going to higher energy, going to higher precision at low energy. And so by making very accurate measurements at low energy, you can start to put constraints on what are the possible extensions of the standard model to putting constraints on possible extensions to the standard model. And I've included here some examples, things like the electron-electric dipole moment that, according to the standard model, that should be zero. But if you look and perform high-precision measurements, perhaps we'll see a deviation from the expectations of the standard model. And so that's the one motivation is looking for new physics beyond the standard model. And the other is, see, I got it partly. Still don't quite have the feel of this. Oh, there we go. Okay. The second is applications to plasma physics and astrophysics, where there's just an ongoing urgent need for high precision atomic and molecular data. So spectroscopic observations of line intensities together with theoretical data determine the temperature and pressure conditions inside a plasma, and especially a controlled fusion plasma, the tokamak type of device. Tremendous need for basic radiative processes, oscillator strengths, Einstein A coefficients, collision cross sections. And so this is the second motivation for why basic atomic physics is still of interest. So let me just go on then to what do my students do? Research consists of a combination of mathematical analysis with numerical calculation to find wave functions that are essentially exact for all practical purposes. This then provides the foundation on which to build these higher order corrections, including the effects of relativity and quantum electrodynamics, and then to compare with high precision measurements at laboratories around the world. So we work very closely with experimentalists at places like Triumph in Vancouver, Argonne National Lab in Chicago, GSI in Germany, University of Washington. These are the experimental groups with which we collaborate very closely to provide the theoretical data to interpret the experiments. So what do? As I say, Professor Emeritus, gives me more time for research. I'm also principal of Canterbury College part-time. So when I'm not here, you can find me at Canterbury College. Usually I'm there in the mornings and then here in the afternoon. So you can find me at either place. My office is right next to Dr. Rangan's, 277-4, just around the corner here. My students sit in the office room right next to the conference room. My webpage, you can find out more information. If you just Google Drake and SharkNet, that will take you to my webpage. Also, I just finished giving a whole sequence of lectures in China, in Wuhan, and those lectures are now available online, so you can hear me talking about all of this in great detail. So please contact me if you're interested in doing theoretical atomic physics. My email address is just gdrake@uwindsor.ca, Gdrake. And so that will bring you into contact. So thank you.
Thank you, Gordon. All right, we're almost done. We just have Dr. Xiao and myself yet. So I'm interested. And then the students will be talking. So make sure you, very valuable contribution from our students here. I should point out while Dr. Xiao gets this set up that after one of the things, we've already given you some advice on what to do. Look at our websites, send us email. But if you're not talking to the older students, you're missing out on a huge resource, right? So just Dr. Drake mentioned, so sitting at the back, so Aaron and Javier and Victor are all doing research. Up the front, Matthew and Xiao and Travis and Emma. So if you're not even talking to them, you're just missing out on a huge resource. That should almost be your first stop. Like, what's it like? Drop by the Physics Club room. What's it like? How do you fit in time in the week? They're going to talk about some of that today, but they're your best source of resource, as well as this other thing. So.
Hello, I'm Xiao. This is my research group. I have Bio is my graduate students, and all the others are undergraduate students. And Tristan and Mark are going to be graduate students in the fall. So we do MRI research, magnetic resonance imaging. So if you first heard of this, you're probably thinking about MRI in a hospital. And our MRI machine looks like this. This is our shiny core lab in the core. And we have a very nice glass window wall. You can look right into the bridge to Detroit. And I could spy on my students from the street to see what everybody's doing. This is our scanner. It's a small animal scanner designed for mice and rats. Rebecca is on her knees, so you can see the scale of the scanner. It looks much smaller than what you would expect in the hospital, but we could do more powerful things with this. So this is the mouse image taken with our scanner. It's a pretty standard way of imaging, looking into a biological system inside of it. But we, of course, do more than just that, because MRI is so powerful compared to the other imaging modalities, such as X-ray, CT, and PET, because we could create very versatile soft tissue contrast. This is an example with an egg. So this is intact, the whole egg raw. We took a slice in the middle, so you can see the different contrast between the yolk and white and the center of the yolk. And for the same experiment, if you just change the parameters slightly, you can reverse the contrast. So you can make this part brighter and the other part darker. Or you can have an image like that, because all the MRI image, in this case, the voxel intensity is a complicated function of a lot of parameters, the proton density and some MRI parameters. These parameters give you information on the molecular level of tissue structure. So what we do is to create novel experiments to explore this dimension and do more quantitative study of different biological or material systems. So we don't just click the button and get an image. We create new experiments. This is Leo. She will talk to you very soon. I'm looking forward to her talk. So in most of the MRI research group in the world, you don't get to create your own experiments. So Leo has created quite a few of experiments from scratch. It's not an easy process. You have to learn the system very well. You have to debug the pulse sequence and see why things were not working with some effort, but it's a great learning experience. Once it works, you'll be very happy. That's what she looks like. Okay. We also do novel image reconstruction and data processing. So once you create a new experiment, you want to process the data and get an image, because MRI collects data in the reciprocal space. So that's what we do. This is what Mark is doing, showing us his new algorithm to process the image. This is his undergraduate thesis project. So Mark is here. He used dictionary learning to accelerate the data acquisition so that the speed of imaging could be faster, and also he does the automatic separation of image features. This project is in collaboration with a German group. They are studying some cell tracking for some disease, but they really struggle with their temporal resolution. That's why we propose to accelerate the acceleration with some advanced technique. And also, they are counting the cells in the brain manually, which is a huge burden. So we say we could help them do the automatic separation of image processing. This is another student, Tristan. He has been using machine learning to process the MRI data. This was his presentation last year in the Funk Undergraduate Research Conference. His work has won the first place poster award, and this work is going to be submitted to a peer-reviewed journal. So another stream of our work, so that is a small animal scanner. We also work on portable MRI. As Dr. Maev said, usually you don't bring the MRI scanner to the battlefield or other places, but you can bring this to anywhere you want. That's what we are developing, and that's very low cost compared to $1 million scanner. But it comes with some adverse conditions because we have low field, we have inhomogeneous field, and we have a limited detection depth. So we're doing a lot of hardware-related development and advanced signal modeling to try to make this as useful as possible. So we have hardware-related research. That's what Jean-Marc does. Not only smashing things, but he built this 3D field mapper. Basically, it's a similar principle as a 3D printer. So he used a very cheap Arduino controller to control the arm so that this probe could be moved around in the space in a controlled way. If you buy a field mapper like this commercially, the cost will be more than $50,000. But he managed to bring the cost down to below $10,000 just by doing all the components himself. So this is a very great experience for you if you love to have hands-on work to get your hands dirty in the lab. Another hardware-related project is Rebecca, that she's holding a probe. So this is to generate the oscillating magnetic field in order to excite and receive the signal. What she is doing is to build her own probes, the coils, so that we could incorporate that in the portable. We could optimize the field in the portable scanner and also create coil that could work with different nuclei for this instrument. Her first prototype looked like this, but it's going to be very beautiful very soon. So basically, she's creating something like this. Okay, in summary, we provide lots of hands-on experience. As I said, if you're in a different kind of MRI research group setting, you would not have so many hands-on experience on the instrument time because they charge you $500 per hour. So let alone creating your own experiments, you don't even get to push the button to run the experiments. If you do human study, you sit next to a technician who pushed the button for you, and you are given the DICOM image and go home look at it. We also have these hardware-related work, as shown. In our group, we emphasize a lot on math because we do data processing and image reconstruction, and computer programming because you program your own experiment and process your own data. And we encourage a lot of your own ideas. If you think, oh, maybe this is a better way to do things, we like that. We also have very good peer support. You can see the nice smiling faces from my students. I think that's all. Thank you.
And so, Dr. Xiao, what is the best way for them to find you?
Oh, you can find me in the core lab or my office over there. I also have a lab in the basement. Yeah, my office might be. And my email is just my full name at UWindsor.ca.
Okay. All right, then I will just try to finish us up here. So my name is Steve Rehse. I'm an experimental physicist, and basically I'm concentrating on pulsed laser spectroscopy is what I do. It's not very dissimilar from what Dr. Hammond does. He and I are both, I guess, laser physicists, you would call us. The time scale of what we do is a little bit, I'm a nanosecond person, so about 1 million times slower than Dr. Hammond. But basically we use very intense nanosecond pulses of laser light. Here's a drawing, it looks like this. It means we ablate or blow up a variety of targets. My student Dylan used to say, why wouldn't you want to work in a laser lab where you get to blow things up with lasers? Because that's really what he liked to do. And he's like, people would ask him, why would you do it? He's like, why wouldn't you want to do that? And then we perform high-resolution optical atomic spectroscopy. We look at this microplasma, and we look at the colors coming out of it. So I'm a laser person, and I'm a spectroscopist, which means I think a lot about light and what the colors of light tell me about the compositions of things. So this is kind of a schematic of what it looks like. This is what it looks like in the lab. I'll be able to show you a video of that in a second, I hope, but just in case. This is the laser is invisible, so you don't see it, but this bright light you see flashing, that's the plasma forming. It's about 50,000 Kelvin, so it's a very bright source. You can easily see the light coming out, and we just have very sensitive equipment which looks at the light, and it's being collected by an optical fiber here. So all the experiments I do are a really interesting mix of, I'd say, laser physics, atomic physics, plasma physics, and spectroscopy. It's all in that general category to lesser or more extent. Everything that we do, this idea of exploding a target and looking at the light that comes out of it, we call laser-induced breakdown spectroscopy. That's really what I do. It's LIBS, L-I-B-S for short. That's what I do. So if you do LIBS, what can you do with that? Well, it turns out you can do a lot of things. This is the Mars rover Curiosity. On Mars, they use LIBS to analyze rocks and soils, right, at distances of up to 7 meters. So this is a mock-up of the Curiosity, but it looks just like this. The Curiosity has a chem-cam up on this masthead, and it's shooting out a laser, and it's driving around Mars, and it's analyzing these rocks. So rover moves very slow, Curiosity. It has to stop and picks things up from the belly, but this laser is the only instrument on board that allows it to go to standoff distances and sample, and it's accumulated well over 100 times more data than any other instrument package on the entire rover. Because it can look around, and then if it sees something interesting, it might go over and then use its other probes to analyze that thing. I'm not doing anything like that Mars thing, but that just tells you what the technique can do. What we're doing is kind of concentrating on pathogenic bacteria. That's really been what my idea was, if you take that laser and it blows something up, what if the thing that you're blowing up or ablating is pathogenic bacteria or a clinical specimen? So my lab is biosafety level 2 approved. And we're looking at bacteria. We grow and culture our own bacteria, and when you blow it up, and now it's just been reduced to its atoms, it gives off light, and can you then identify that pathogen on the basis of that light? So we call that a real-time point-of-care medical diagnostic technology. Our idea being, when you're sick and you go to a doctor and you have some bacterial infection, can they take a specimen from you right there and put it in one of our instruments, and it can tell you what you're sick with, what pathogen. That does not exist anywhere in the world yet. We are trying to invent it. That's the work. It's a lot of work, but we're getting there. So the door of my lab says it's biomedical physics, because it really does have that biomedical connotation. Anything medically related, we're interested in shooting. These are some of my groups. So this is the current group. So Emma is here today, and we'll talk to you. My graduate student Jeremy is here. Sydney is another student currently working with us, and then Chris and Paul have graduated, and Allie was my former graduate student. I like this picture, which I took a couple summers ago, because I use this when I talk to the high school kids, because I realized in this picture, which is the students in my summer lab, we have a medical physics student, a physics and math student, a physics and computer science student, and a pure physics student. And they're all working in the same lab. So it doesn't matter what you're interested in, or if you're combo this and this and this or whatever. You can work in any of these labs. And I realized they were all in my lab, all doing different projects. Different bits. The guy who is physics and math, I'll give him a little more math. The guy who's physics and computer, I'll give him a little more computer. So any one of us, when you talk to us, there are aspects to our research where we can tune it to what you want to do or what your strengths are, right? So don't ever think that even though what you've heard today is one size fits all. It's really not. We will try to figure out what it is you're interested in doing, and then can we do that to the best of your ability. So if you want to learn more, we have this YouTube video, which I was hoping to show, but I don't know. So this is, I do want to proceed. So this is, yes. So this is Sydney Sleeman. So I'm not going to show all, it's only 4 minutes. I'm not going to show all of it. I just wanted to show the last bit of it, if possible. I didn't have time to get the internet going before, because Dr. Kim was in here. So if we don't have time, I won't show it. You can just go to YouTube and just look for Rehse Biomedical Physics Lab, and you'll see it. because I probably can't. Who knows their passwords anymore? Right? Like none of us. So at any rate, let's not mess with that. So if you want to find me, here's Sydney. I just wanted to stop because this is a really, really funny point. It's only 3 minutes 58 seconds long. So please go home tonight and watch our little video, which the students and I just shot, and my student Archie Martinez mixed on his computer. It's really, really super funny. I just wanted to show this pic because if you want to find me, you can come up to our laser lab, which is 390-2. And in this frame of the video, Sydney's going, oh, this looks exciting. We got some danger, red light danger going on here. Let's go inside and see what's happening. And just opens the door and walks in, which please don't do that when you see our danger light. That means you're not supposed to come in. So, but then we have the laser flashing inside. So you can just look at that, and then you'll basically know what we do. Emma gives a very nice description of her pathogen stuff, and the other students are there talking about it. In 4 minutes, well worth your time. Okay, I'll just stop there, and then I'll turn the floor over to the students. So why don't you guys come up here so the video can kind of see you. And I will let them, they don't really have anything specific in mind. Wait, I'll do this and I'll make the screen black behind them because I don't think they have anything to show, but I will mute that. I'm going to get out of the way. So just introduce yourself and say something germane to what they would like to hear.
All right, hi everyone, I'm Travis. As you know, I work with Dr. Hammond. I started in my second year, first semester. Originally just as a volunteer, and then so my entire second year was just volunteer. It wasn't until the summer where he offered me a summer research position, so that was great. I've done a few things. I've worked on a time fountain, a couple of small projects such as using both of them using Arduinos. Actually, I built an ADC, so an analog to digital converter, which is kind of like it takes an analog signal and it kind of converts it to a digital signal that a computer can read. And we use that to just read signals from different things, kind of like an oscilloscope. So I made like essentially a very cheap version of an oscilloscope. And I also just built just a laser safety sign like you saw on Dr. Rehse's door there. I kind of just built one of those in Arduino as well. And now, so I've kind of moved on to something a bit more difficult. I'm working on like experimenting with laser diodes. So typically these lasers that we use in our research labs are very expensive. I'm just trying to find out ways to use just like cheap laser diodes you can find online. So for example, the one I have right now, it's just a 1 watt laser diode. I think it was about $250, so that's like really cheap compared to some of the things that, the bigger lasers. Obviously, it's not going to be as high quality, but we are still looking for like applications with those. Another thing is, my first semester, I started with Dr. Rangan, and then I kind of doing like a joint project with Dr. Hammond. I was working on like computer simulations with Dr. Rangan, but as I started doing things with Dr. Hammond, I realized, I'm kind of more experimentalist, right? Like I like to work with my hands, doing that kind of thing, working on circuits. So obviously, don't be afraid if you do like start working with someone. Don't be afraid to keep looking around and possibly switch and start working with someone else. It's really they're not going to be offended or anything. It's not a big deal. Definitely make sure you kind of look at all your options, find something that you definitely enjoy doing.
Good.
Yeah, thanks.
Okay. Hi, I'm Emma Blanchette. I am third year undergraduate. I started working with Dr. Rehse in my first semester of second year, and I was actually an OS student. Are any of you here OS students or applying to? No? Yes? One of you? Good.
You should
Please
apply.
You really should apply. It's awesome. So anyways, I started working as an OS student with Dr. Rehse, and the project that myself and Sydney Sleeman worked on in the first year, because we both worked with him then, was identifying contamination in our bacterial samples and using the laser to try and identify that contamination. And fortunately enough, we were actually able to get a poster out of that with our master's student, Jeremy Marvin, and that poster went to the CAP conference in the summertime and won 3 awards, I think, right? So we won 3 awards on that poster, and this year I've actually started working on a bit of a different project, which is the classification of different pathogens. So when we shoot them with the laser, we get all the data back with all the spectroscopic lines, and what I do is I take that data and I analyze it and I find the best way to classify it or the most efficient way to classify it. So that's kind of what I'm working on now.
Can I just stop since you've had 2 people? So we've heard about like people programming Arduinos and firing lasers and looking at pathogens. What do you need to know when you come into these labs? How much of this stuff did you know when you started?
None of it. None of it.
So
You
yeah.
learn a lot. You learn quite a bit, and you can come in with almost nothing and pick up a lot within like the first couple of months. You definitely learn a lot of new skills. Like I learned Excel, and now I'm really, really good at Excel, and that's obviously transferable to other jobs, right? Then you can learn other hardware skills like Travis did with circuits. So you can really get a lot out of it, depending on what you're looking for.
Yeah, like when I first started, I had like no experience with like working with Arduinos or anything at all. Obviously, that was like second year. Now, like in third year, you guys actually they might be moving your program, but I took like a circuits course, and I'm finding like now I'm like starting to use things I learned from that course. So I mean, obviously, as like you go up in years, you start learning things that you will be like applying to your research. But yeah, at the beginning, like I didn't really know anything at that time. I really just learned as you went.
So I just want to comment. I just wanted to point that out because I think it's really important. You know, we want you engaged in doing the research so you can help us with the research. But as I like to tell the grade 12 students when I talk to them, these things are talking about being able to program an Arduino, just being really good at Excel, knowing circuits, being able to program. These are transferable skills. Emma said that. I'm always pleading with students when they're in the high schools before they consider coming to us. Yes, you're all going to get a degree. Everyone on this campus is going to get a degree. What can you do? What can you do that someone's going to give you a job for? I think people are just convinced, I have a university degree, somebody's going to give me a $150,000 a year job. To do what? Sit there and take notes in a class? No, skills. These are, and it's not that the classes aren't useful because they're super important, but the stuff you're doing in each of our labs, real skills, you put them really on your resume. And you don't even know that it's going to be valuable, but the stuff Travis was doing, that programming Arduino, like most of us can't even do that. That's awesome that a student can do that. And I don't know what it's going to be useful for, but that might be the thing exactly that an employer wants. You just don't know. So it's okay that you don't know what the skills are. Say yes when your prof wants you to do something. Do you know how to do it? Nope. Are you willing to try? I will just learn. I will learn it. Look at it as a challenge. Look at it as a skill you're going to master. It could be very useful to you. So it's like a fringe benefit that you're going to be getting from these things. So useful.
In fact, that's the single most important thing you should learn from a university degree is how to teach yourself.
Yeah, because I would say students are always coming to me in their fourth year. It's like, well, Dr. Rehse, now I'm looking to get a job. How do I get a job? And I was like, well, what can you do? What do you do that someone's going to employ you for? Well, I don't know. I never thought about that. Well, what were you doing during those 4 years? You got to be picking up some skills as well. So when you're in the lab, this is just coming along for the ride. It's so great. So sorry, that's in the middle, but maybe these guys can think about actually what they're doing and how that's really useful.
No, I'm actually glad you mentioned that because in my lab, the most useful skill that I've learned is programming, actually, and critical thinking. And so my name is Layala. I'm a graduate student, first year master's student in Dr. Xiao's lab. And all I do basically is set up a computer and program. And I program experiments and I run the experiments, and as she mentioned, they don't always go right. Most of the time they go wrong. Probably about like 90% of the time they go wrong. And when that happens, first I get a little frustrated. Then I ask, why did it go wrong? And then I sit and think about it, and then I, try to isolate the one variable that's causing the issue. And that's where the physics degree comes in, because that's what we're trained to do. We look at a problem, and we break it down, and we try to figure out where exactly the issue lies. And then we use our critical thinking skills, what we learned in physics, and fix the problem. So a lot of the things that I do in the lab is basically just that. Yeah, sure, I picked up like a few languages on the way, like Python and MATLAB, which are super useful, super widely used in industry. But the most important thing is how to use them and how to break a problem down and solve it, which not a lot of programs can do. Physics is really well known for that. You do it in every single discipline in physics. I just decided to choose MRI because I like math and I like computer science, and I also really like that it's a very unexpected application of quantum mechanics. So you wouldn't expect quantum mechanics to be like an imaging thing, but it is, and that's why MRI works. And I just find that very fascinating and very cool. So yeah, that's pretty much what I wanted to say.
My name is Matthew. I also work for Dr. Xiao, and I just recently finished all my courses for my bachelor's in medical physics, so I'll be graduating in May. I started working for Xiao almost 2 years ago. I started my undergraduate research with her, and now just recently I'm working as a research assistant. So I I started doing theoretical work, so I was using MATLAB software to create simulations during MRI artifacts, but eventually I wanted to do more experimental work. So another project I did was I was in a lab. I was creating a series of samples from scratch, and I was measuring. I was trying to identify any statistical behavior with the data. So so my research now focuses mainly on MRI for quantitative analysis. So using MATLAB software, we have a series of scripts, and we in the lab get some whole sequences that were made by Dr. Xiao, Mark, and also Xiao, and I run them on these samples. And it depends on the goal of my project. Like right now, I'm working with glucose. I mix it with egg whites, and egg whites, they're rich with these proteins called alpha-albumin. And right now I'm trying to do a quantitative analysis of the effects, because the goal of my project is to see if there's a possibility we could actually diagnose a patient with diabetes using an MRI instrument. So that's what I'm working on right now.
Okay, just one last thing I want you guys to talk about. I don't want to keep you guys too long because I know you probably have to go, but I bet the students are thinking, so if you can just comment on one, they're very, very, very busy, I'm sure, right? Because the number one barrier here for students not getting involved in research is you're busy. I know you're busy. We all know you are. 5 classes, labs, all that stuff. How on earth are you going to find time to do research during the semester when you're taking all those classes? It'd be so easy to say, I'm not going to do that. I'm just going to focus on my classes. So how do you do that? I mean, can you talk about the time of it? Because for sure it is more time, but is it worth it? And then how do you find the time? How do you manage that? Because I'm sure they all sounds great to them, but then when it finally comes time to make a decision, no, it's just too much work. I'm busy. You're all busy. Everybody's busy. So how do they do it? How do you do it?
I think it's just like important to always like, obviously your classes are really important too, but I think research is like just as important. Like Dr. Rehse was saying, like once you graduate, it's, if someone's, you're interviewing for a job and someone's looking at like 2 applicants, oh, this person only has like, their coursework. This person, maybe their grades aren't as good, but they do have a lot of like research experience. I think it's likely that a person with a lot of actual experience doing things would get picked. And it's just, yeah, I mean, it is hard. It's a lot of work, but it is very important. I would say just as important as your courses to do research. And yeah, I mean, there's lots of ways you can get paid for it too. So maybe like if you already have a part-time job right now, maybe consider, if you do find a research position and you can leave that other part-time job and do this instead. It's definitely worth the time.
Okay, so jumping off of what Travis said, you definitely need to have like the drive or some goal in mind in order to really want to do research. So like he said, maybe you want to leave a part-time job and get involved in something in your field, and that's really good. Or, maybe you really want something to look good on your resume. So you should definitely have the drive before going forward, but the best way I found to fit it in my schedule is like put hours in the lab between classes. So if I have like a 4-hour gap, I'm going to be in the lab for those 4 hours working. Or if you're an early riser and you get up at like 6 or 7 a.m. for some reason, you can come in early at 8 and you can work until your classes start. Or if you go to bed late, you can stay kind of late and keep working that way. There's definitely time in between classes and in between other activities that you can find, an hour or 2 to put in the lab if you really want to do it. So that's, I think, the best way I would say to schedule it is just look for those gaps that you need to fill in your day.
So going off of that, I think it's important that you talk with your potential supervisor, and see what they expect from you first. Like, do they expect 5 hours, 10 hours, a week? That sort of, just set that line first, and then meet the line that they set. Time management is important no matter where you go, either a job or school or anywhere. So when you are in university, especially in first year, time management might elude you. It might be really hard to manage your time effectively. And so learning how to make timetables, how to schedule all your hours is really important, and then stick to the schedule. Don't, I guess, get lazy, or don't say, oh, maybe I shouldn't go to this one class and do research. No, stick to your schedule. Don't stray from it. And also, I think it's, as Emma said, it's important to have a goal in mind. You want to come into the lab, to do something, not because you have to come in. I think that is probably like 90% of the battle, just having motivation to go in there. And well, I mean, I'm not saying weekends are a thing, but if you really want to get some work done, there's always, the weekend. Maybe if you're at home, you can do a literature review. But the most important thing, I think, is to set up like a timeline with your supervisor and talk to them and see what they expect from you and what you can do to meet those goals. Because if you're doing a lot but it's not necessary and you're cutting hours from other things, then they could probably work with you to make a more balanced schedule, I think, which is my advice. So that's what I think.
To make a comment, this is something that nobody else has touched on, and at this stage, if you're a first year or second year student, all of physics is pretty similar, right? Because everybody takes the same physics, so you really don't have the specialization knowledge to pick one field over another. So I wouldn't really stress about saying, oh, I really want to do atomic physics, or I really want to do astrophysics, or whatever. It will come, because at this point, you're learning skills that can be used anywhere, right? But the other thing is also that, yes, finding time to do research is hard at the beginning, especially if you are working. We usually say don't work more than 10 hours a week, other than your classes if you're doing full-time school, because otherwise your grades are going to suffer. But then, not only the job, not only requirements for the jobs, but also for graduate. If you're planning to go to graduate school afterwards, anytime you have a co-op, a service learning internship, undergraduate thesis on your transcript, that gives you an advantage for scholarships and for graduate school. So if you have two students, nowadays most employers don't ask for your transcript. So whether you're a 90 student or an 80 student may not matter that much. But at the same time, if you have those experiences, you have co-curricular transcript or a letter from a research supervisor that says that you have really good work ethic, you have all these skills, that's a huge advantage. And really that's what doing undergraduate research or any other form of experiential learning is about.
Just one comment before I move on to Matthew. I just want to say Windsor has the best undergraduate research in all of Ontario. I would even say as far as Canada. Because you go to any other university and there are specific classes that students have to take to even do a thesis. Like they don't, unless they're the top of the top, they don't typically get into research labs as early as first year. So, this is probably the most amazing opportunity you will have to do research at the undergraduate level. So I think you should take it and don't look back and get as much as you can out of it. At the Fun Conference that Tristal went to, I was also there, and we beat most of their students in the posters. And it's Western, right? You would think, oh, big university, they have the best projects around, but for Windsor, and we still managed to get a good place up there. So don't think, oh, Windsor is not that great. No, we're really good actually. So.
That's right. Yes, like what they all said, time is always going to be an issue. When I did my first year of research, I probably did only at least 5 hours per week, not 10. Again, even if it's just part-time research, it's still something good for your CV. Like when you graduate from university, you don't just walk away with just a bachelor's degree, like all the other students. You want to separate yourself from the rest. And for me personally, I learned a lot more from my research work than from just doing the courses, especially programming skills. I didn't know what MATLAB was before I got involved with MRI, and it was really worth it for me, honestly. So even if you can only do a few hours per week, if you can do full time, it's still worth it.
Okay. We'll hang around here for a while if you have any other questions, but it's an hour and a half. That's a lot. Thank you very much for your patience. Hopefully that was useful to you. It's just a start, but you're free to go. And thanks for coming and paying attention. Please tell your colleagues and friends who weren't here. Find more information. Talk to us right now, or just think about it and talk to us in the upcoming weeks, because the first summer's coming up, and summer research can be a great thing for all of us.
NSF USRA applications are due very, very soon, so
USRA applications, applying for
It
outstanding
takes
scholars if
at
you're not
least
there.
10 days to make that application, so get started. Don't wait until the last day before the deadline.
But otherwise, thank you, and let's thank our students for having